is Jason Handley. I'm going to talk to you a little bit about what Duke's been doing with small unmanned aerial systems. We do not call them drones. Drones have a negative connotation. Usually there's a missile attached. And so we like to call them small unmanned aerial systems. Let's see if I can get this thing going. So I'm going to skip this because it's due to time. So we started working in August 2014. We received our first two Section 333 exemptions in March of 2015. June of 2015, and we did our first pilot about 2 weeks later at a coal plant. Coal plants are great, or any kind of generation facility is great because you usually have generation equipment, you have transmission equipment, some distribution, and in our case, we actually had renewable. We had solar farm there also. And so we did the steps through. We ended up doing a wind farm. And then in October of 2016, we went through our small unmanned aerial systems training. And so after Section 107 came out, or Part 107 came out, we actually decided to train our own internal employees to this. We'd been hiring it out outside companies. And what we found was the fact that our own internal employees really wanted to be able to do this themselves and have the platform to be able to go, as Kurt said, at a moment's notice and go do what needs to be done. We did our first storm restoration in October, November of 2016 with Hurricane Matthew. And then we actually have created a new department at Duke. So my group is the Emerging Technology Group. We take these technologies and kind of evaluate and pilot them, and then we roll them out to a business unit. In this case, drones were wanted, or unmanned aerial systems were wanted by all the business units: generation, distribution, transmission, commercial renewables. And so the best place for us to put them was under our aviation department. So our aviation department created two new positions, and they actually hired a manager and a flight coordinator to be able to do all of our UAS flights. A couple of myths about UAS: it's not a toy. They are assets. And this is really not an emerging technology, as we've heard today. I mean, this stuff has been going on for a long time. And as Kurt kind of mentioned there at the end of his presentation, we really see this, we have three pillars of this technology. One is safety. So if we're going to be using these, we ought to be using them to augment our safety procedures or either replace an existing operation that we had to do manually. Operational excellence is from the standpoint of being able to save cost as well as do it faster. And then the business case for us made a lot of sense, again, to pull this internal to Duke Energy. So we have a couple of different platforms. We have about 30 different units, about 6 different platforms. All of our foreign-made platforms have been grounded by our own cybersecurity folks. So the only thing that we can use are either American-made or European-made platforms right now. So we're using the Aero Environment Shrike. The Arion Sky Ranger is probably our go-to right now. And then, of course, we have the Puma also for longer duration flights. So for some of the training that's going on, this was originally wanted by our commercial renewables groups. They have to do large solar field inspections as well as wind farm inspections. So we trained 13 employees from the renewables group, 4 from aviation, and 1 from our craft and maintenance section from distribution. We put them through flight school. Flight school entails ground school with a written test. And then you also have to go out in the field and fly them yourself through hands-on training. The new manager of UAS as well as the coordinator have built a really good program now around these unmanned aerial systems for Duke. So they've created standard operating procedures, a safety management system, the aviation use policy. So even though we have our own pilots, even though we have our own platforms, we still have contracts with third-party vendors. And those contracts have to be vetted through our risk department. So they've put together all these different contracts as well as procurement language when we go out to buy UAVs. So that I want to really give a great shout out to those two guys who've been working themselves to death. The ground school, again, we teamed up with the Unmanned Safety Institute and went on an online self-paced training. through multiple different factors, airworthiness, human factors, and then of course you got to know the rules, especially what's going on with Part 107. And then for the in-field training, we went out and we actually let them fly the different platforms that we use. If you could, on the right hand picture, if you could start a video just while I talk. So what really turned us to think about these as more of an operational tool for us is the fact that we have, North Carolina is, we're in 6 different states, but North Carolina is the second fastest solar growth state in the United States. And so we are looking at and managing a tremendous amount of solar. And in the past, what we've been doing to inspect is we'd be walking 5 megawatt solar fields and going and look at thousands of panels and connections and seeing if we could find problems there, checking voltages every so often. Well, what we found was as soon as you put an infrared camera on a drone, what used to take 3 days takes about 2 hours. So there's operational efficiency there. There's also safety aspect there because now you don't have people walking around with overhead objects like solar panels that they could potentially hit their heads on or slip, trips, and falls. So we really started in the spring of 2016 looking at using IR to do a lot of these inspections. This makes a big difference when you go to farms that are 32 megawatts, 85 megawatts, hundreds of thousands of panels, and the time it would take you to go out and actually walk this. So we're seeing a tremendous operational impact from being able to do this with this type of drone UAS technology. One of the challenges that you run into, though, is once you start mapping areas such as big as that, you're going to find that in 2D orthomosaic, you're going to get lost because if you're taking video, that's one thing, but if you're taking individual still pictures, you got to piece them together. And there is no kind of bottom XY plot to really say this is where you are. And so we're having to do 80% overlap on both the front and the side at about 120-foot height to really understand where I'm at in that solar field as I move along. And I didn't point this out on the video or in this picture, but you can see failed cells by the light color. They look white. So if you see white patches, those are cool patches, all right? So they're not actually generating any electricity. So you could see whether it may be a cell, whether it may be a string, or you could have an entire section out where you might have to go look and see if the inverter's even online. We use a really good mapping program called Pix4D, and it is a great, and I don't know if you can see it, but that is a complete string that's out. Yeah. And then you have a couple of cells that are out over here. But again, it's really the mapping of that, of the video that's been taken and getting it into a program that you can actually make sense out of the video and make work orders at the end game to go fix those issues. So where we're headed, though, is doing it with artificial intelligence. So there's some new AI chips being made by Intel and others that are going on these types of platforms. And what we're really wanting to do is go through these different steps. And, I guess I can read these steps to you, but really as you go through, you collect the images, and then you want to see some that have failed and some good panels. You're going to identify those types of panels, and then you're going to run it again. And it's somewhere between 200 and 300 images to train the platform on what it's looking for. And then you actually run it. You put the platform up in the air, and you go through and see if you can identify it. And then for any failures that are not recognized, that then becomes a new add to the training set. And so we're starting to work on that now with this program to where we can go in, and these 2 pictures are nothing more than our first attempts to start using a little bit of artificial intelligence and it tell us where they think failed panels are. So we're not there yet. This is not a commercialized, proven commodity for us, but it is where we want to go because we spend a tremendous amount of time looking at video. It's still a lot less time than we did when we were patrolling and inspecting by hand or by foot. But if we can make this work with the artificial intelligence to actually see where this is actually failing, it recognize it, it create the work order, it's going to be a lot better for us as we go forward. So wind turbine inspections are done on a normal basis for us. We used to do them by rope access, which is, I'm not going to say the safest thing in the world, ground inspections with high-powered telescopes, or either doing a remotely controlled robot. So We're talking specifically about UASs now, but we have a lot of different crawler robots. We have underwater UAVs that we can go inspect our dams, inlets and outtakes from our generation stations where we suck water in. And then we also have some military-grade drones that we use inside our nuclear plants and get into high contamination radiation areas that we don't really want humans to go very often, that are all remotely controlled. But we found a lot of good uses for them, especially with wind. So you can see cracked blades where you're starting to see cracks in blades, and then just bird strike damage, or if I'm not sure if that looks more like a metal strike damage to me than bird strike. But it's good to be able to have this type of platform. You know, what Kurt talked about with looking at coal, with looking at the gravel, we do the same thing with coal. So we go out and measure our coal piles. Even though our coal piles are shrinking because we're shutting down coal for the most part as a generation source, we still have it today. And so what we look at it for is we look at it to see when is that next trainload of coal going to be needed, and can I better utilize my supply chain by knowing what my limits are, because I have to be mandated to have an X amount of day supply in case there are disruptions. So we use some volumetric measurements with the drone to go out and really look at these different coal piles. So we use them a lot, flue gas, FGD stack inspections, so where we can go up and we can see things as small as a bolt that's becoming unhinged, and that's at a 400-foot height on some of our larger FGD stacks. And just places that you don't, places that you just don't want to put people. I mean, you don't want to either build scaffolding, or you don't want to put people on the outside of those types of situations. And again, trying to do that from the ground with a high-power telescope, maybe you can, maybe you can't. So we did a lot of hurricane response too. We actually had to talk our emergency management people into letting us use drones for hurricane response. They thought it was just a novelty and we would get in the way. Within the first day, we proved the value of it. This is from Hurricane Matthew. And I think if you could push the button on this one too, I'll talk as this one. There's not a lot of damage in this video, so there's not a lot, but I mean, it can show you with Hurricane Matthew, really what we were able to use it for was we had a tremendous amount of flooding in North Carolina. So we couldn't get in to do damage assessment like we normally would because we couldn't get in, all the roads were closed. So what we did was we set up drones on the edge of roads that we could get to and then ran them as far as we could without being outside of visual line of sight. And so what it allowed us to do is it allowed us to get a head start on the damage that we could find once the water receded. So we didn't actually have to, the customers have already been without power, they've already been flooded. Once the water recedes, all they want is their power back on. They don't want you to have to come in and say, oh, I've got to now do damage assessment. So this was a great help to us in that response. And here in Florida, in Hurricane Irma last year, we found them extremely valuable. And here's an orthomosaic shot more along the lines of doing the mapping and seeing exactly how far off the towers are from each other and the distances that you have. I'm going to go ahead and speed up just because I know we're kind of out of time. So we use LiDAR also. LiDAR for us is a tremendously valuable tool. We're doing it not only for looking at potential for sag in between our conductors. Sag for our conductors is something we have to pay attention to because sometimes with wind you get galloping, and sometimes if the sag's not right, the conductors can slap into each other. It's called an aileron effect, but don't really worry about that. But anyway, you just want to keep the sag apart enough so we can actually measure that. We can measure height. We can measure how far trees are away from our lines, and I think that's kind of, you can't see the tower in this picture, but you can start to see there's 20 meters away from this side of the tower, that side of the tower. And why we're looking at that is because of the danger objects that potentially can fall into. So you see here that we've identified a danger tree that could be dead. It could just be too tall. We're not exactly sure what that was yet. More than likely it's dead because of the different coloration, and that danger tree could actually fall into our line, so we proactively can go out and take that down before it has a chance to actually get into our lines. So I went through that relatively quickly because I wanted to make sure that there was a time for questions and answers, but thank you for your attention.